In this equation number 5, this is a scalar, this is a vector quantity, this is a gradient operator, and this is another vector quantity, and this is scalar quantity. Okay, here I will substitute instead of P, I will take it as a vector quantity dot product dot this gradient operator, and this is scalar quantity, scalar function f. Okay, here the substitution I'm going to make here is P r prime a is equal to P r prime, and f is equal to 1 by r minus r prime. Okay. Now there is an identity. The identity is this one. If I can write this term as a dot del prime f, then we know the identity, that is del prime dot fa is equal to f del prime dot a plus a dot del prime f. Since this term is a dot del prime f, that is this term, if I take this term to left side, del prime f is equal to del prime fa minus f del prime a. Okay, a dot del prime f, which means P, capital polarization vector P r prime dot del prime by 1 by modulus of r minus r prime is equal to del prime f is 1 by r minus r prime, this vector a is nothing but PR P, capital P r prime minus f is 1 by r minus r prime, next del prime dot vector a. Okay, actually we were calculating that the total potential produced by this polarized object. Okay. Now if I put this is question number 6, then substitute, replace this term by this equation 6, or simply we can say put equation 6 in 5. Then this potential we can write V is equal to 1 by 4 pi epsilon 0 volume integral. Instead of this quantity, we can write this equation, right hand side of this equation, del prime P r prime r minus r prime ditto prime, this ditto prime. Then here it is a minus, but I write it as a plus. Then later I will take the minus with this del operator. This 1 by 4 pi epsilon 0 volume integral. That is I have taken this minus with the minus del p, that is minus del prime dot p r divided by this is r minus r prime d tau prime. Let us say this is equation number 7. Now this is the equation number 7. This equation is the total potential due to the whole polarized object. Remember, we are looking for the polarized material. Looking for this polarized material. And this is the expression V that we obtained is the potential due to this polarized object at the point P. It is at a distance r. Now we use Gauss's divergence theorem to this expression. Use Gauss's divergence theorem for the first term. This first term. Of the RHS of this equation 7. I am going to apply the Gauss's divergence theorem here. That we know the Gauss's divergence theorem. This is nothing but a volume integral. If E is a vector, here del dot E, here we are dealing with del prime, I use del prime. D tau prime is equal to surface integral E dot dA. Since it is a prime quantity, it is a dA prime. Okay. This dA vector, I can write like this one. dA prime and cap. To explain, I have copied the equation number 7 to this page, and the Gauss's theorem also I have written. Here we are going to apply the Gauss's theorem to this term, first term on the RHS of this equation 7. That is here, this E. This is the general form of the Gauss's theorem. Here, since we are using the del prime, I will label it as a del prime, volume as a dot prime, and area as a dA prime, because we are dealing with the prime coordinates. Here this E is nothing but, this is our E. This quantity is our E. Now if I apply this divergence theorem here, I can write 1 by 4 pi epsilon 0, and this volume integral will convert into this surface integral, and instead of del prime E, I can write instead of E, I can write this P, polarization vector P r prime divided by r minus r prime dot. This dA I can write in this fashion: dA prime is equal to magnitude A prime vector n cap, where n cap is a unit vector perpendicular to the, if this is our polarized object, larger number of dipoles are there, and this is a n vector. This is a vector, unit vector perpendicular to this area of the polarized object. Okay, therefore this I can write dA prime n cap plus this plus 1 by 4 pi epsilon 0 second term, then this term as it is, no change, minus del prime dot P r prime divided by modulus of r minus r prime. Let us put this is equation number 8. If there is a surface charge sigma in this polarized object, and the volume charge density rho, the potential due to these charges. We believe that there are some surface charges induced because of this polarization, and the volume charges induced because of this polarization. And if such charges are present, then we know the potential due to the surface charge distribution, that is V is equal to 1 by 4 pi epsilon 0 integration of rho dV divided by R, because we know the potential due to single charge 1 by 4 pi epsilon 0 Q by R. If the body contains volume charge density, then this will be the potential due to that volume charge. Potential due to the surface charge 1 by 4 pi epsilon 0 sigma, this is a volume element. Here we have also d tau, that is why I am using d tau by R. Okay. Now separately we are considering these parts as separate. Separate means, suppose we have a body having these charges, surface charge density sigma, volume charge density rho, then potential at a particular distance R, what will be that potential due to these sigma and rho charges? That everybody knows. Okay. Now let me write the few words here. We can write, or if there is a surface charge is sigma and volume charge means volume charge density rho, then density in this polarized material, we can write the potential. We can write the potential of the polarized material. Potential V is equal to 1 by 4 pi epsilon 0. Potential due to the surface charge distribution, that is surface integral sigma. These charges are surface charge density, that is the charges are to the prime coordinate, therefore R prime. Area also primed one. These are the source charges, R minus R prime, because these charges are to distance of minus R prime, d prime, plus, actually we have already mentioned why this is R minus R prime. Thus surface charge density sigma, volume charge density rho, these surface and volume charge density produces a potential at the point P. Therefore the distance from the charges can be taken as R minus R prime. Okay. These are the charges contained in the surface area. Sigma is surface charge contained in surface area d prime. Similarly, rho will be the volume charge contained in the volume d tau prime. It is 1 by volume charge density is 1 by 4 pi epsilon 0 integration over the volume, that is rho primed coordinates by r minus r prime. This is d prime. Let us say this is equation number 9. Now see, both equation number 8 and equation number 9 gives the potential at the point P. Equation number 8 is due to the potential at the point P due to the polarization, and equation number 9 is the potential at the point P due to the surface and the volume charge distribution that arise from the polarization. Okay, that is, left hand side of equation 8 and 9 are same. If the left hand side is same, obviously the right hand side of the equation will be same. Then let us compare the terms. That is, first one is the surface area terms. Let's compare the first these two terms. Everything is the same, like 1 by 4 pi epsilon 0, 1 by 4 pi epsilon 0, surface integral, denominator r minus r prime modulus dA prime. Therefore, and this term will be equal to this term. Okay. Therefore, similarly, if we compare the here I will write those findings. This P r cap r prime is dot n cap is equal to this sigma r prime. Then if we compare the second term, here I missed this d prime. D prime is here. I missed to write here. Now if we compare the second term, here the plus 1 by 4 pi epsilon 0 is common, denominator is common, volume integral is there, d prime is there. Then we can compare these, and these two will be same. That is, here we can write minus del prime dot P r prime equal to rho r prime. Okay. Now let us copy to the next page. The obtained results are r prime. Now see this equation in general form. That is, I can write in general, this is nothing but P dot n cap is equal to sigma. This is minus del dot polarization vector P is equal to rho. Okay, this P dot n is sigma. Sigma is the surface charge density that arises because of the polarization in the material. That is, if this is our polarized material, large number of dipole moments will be there. Then, because of this polarization, charges called surface charges accumulates on the body, and also volume charge also accumulate inside the body. These charges are not free charges, they are not free to move, so they are called bound charges. These are called bound charge densities. Therefore, I write this polarization vector P dot n is equal to sigma is a surface bound charge density minus del dot P is the volume bound charge density. These are called the bound charges. That is, bound charges are nothing but they are the charges accumulated due to the polarization. That is the physical meaning of this bound charges. I will discuss later. Let me note down this word, bound charges. Bound charges are the charges accumulated due to polarization. They are not free to move, so they are called bound charges. Okay, next topic is the physical interpretation of the bound charges. And just now we have seen that the surface and volume bound charges in the polarized material. Let us see what is the physical meaning of these charges. For this, consider a dielectric medium. Dielectric medium before and after polarization. Okay. The figure, this one is I'm going to write before polarization, negative positive charge centers. Then after polarization, apply the electric field along this direction, then all the charges will be aligned in the direction of the applied electric field. Then minus plus, all these dipoles align in the direction of the applied electric field. The bound charges, we know bound charges are the charges accumulated due to the polarization, and those bound charges are sigma is equal to P dot n cap, and the rho is equal to volume bound charges minus del dot P. Okay. Now after the polarization, if we consider a long string of dipole after polarization, let us consider this thesis. This long string. Here we can see that these are the dipoles, of course. The positive and negative charges cancel. The positive and negative charges cancel. Positive and negative charges cancel. Here also the same happens. Here also the same happens. Finally, only the end charges remains unbalanced. All other charges are cancelled. The only end charges remain unbalanced. So this is a case of uniform polarization. So after uniform polarization, only the surface charges exist. There is no charges exist inside the volume. The one side negative charges and other side the positive charges exist. Okay, that is to have the volume bound charges, the polarization must be non-uniform. Okay, let me note down. That is, after uniform polarization, only the bound surface bound charges exist. If the polarization is non-uniform, suppose if you have a material, the polarization is non-uniform, means there will be minus q charge, this is a plus q, and maybe nearby, maybe larger plus q charge will be here, and minus q charge will be here, and the dipoles may be of different strength. This is a plus, this is minus, and the polarization may not be uniform. This may be small, this may be larger polarization, and this may be larger, this may be larger, this is smaller. If the field is, if the applied field is not uniform, the polarization will also be not uniform. Volume charges cannot be cancelled like this one, therefore the volume bound charges exist, because these two charges cannot be cancelled. From this point, to have volume bound charges, polarization must be non-uniform. Okay, thank you very much.